Welcome to bond polarity and dipole moments. So, an electric dipole is the separation of positive and negative charges. So the electric dipole moment is the electric field that results from our electric dipole. So this is something like a magnetic dipole, where with a magnetic dipole we have a north pole and a south pole, and that separation of poles causes a magnetic field to form around the dipole. So around a magnet, you've got this magnetic field that we can't see with our eyes, of course, but we can observe its effects on magnetic objects that interact with magnets, like iron filings or paper clips or something. So similar sort of thing occurs with an electric dipole. When we have an electric dipole, so if we take a positive charge and a negative charge and we separate them, there becomes this electric field between those two charges, and we can see its effects both on the charges themselves and on other charges that are around. So there are also other possible dipoles, like the magnetic dipole, flow, acoustic, and so on. But I'm going to use the word dipole to refer to just an electric dipole, because in chemistry that's the one that we're interested in. So from here on, dipole just means an electric dipole. So a molecule like HF, hydrogen fluoride, which shares the electrons unevenly and has a polar covalent bond. It has a slight positive charge and a slight negative charge region to it, and this is called a dipolar molecule. It's a polar molecule. It has a dipole moment in it. The dipole is symbolized here with this arrow with a positive tail on it, and the arrow head pointing towards where the electrons are. So this is the negative end of the molecule, that's the positive end of the molecule. And so this molecule has a dipole moment to it. That separation of charge, creating a positive charge here and the negative charge there, that separation of charge causes an electric field around our molecule. Now, a different molecule like carbon dioxide has two polar bonds, and thus it contains two dipoles, because we have carbon dioxide here. Each oxygen is doubly bonded to the carbon. Each oxygen is more electronegative than the carbon is, which means that that double bond between the carbon and oxygen is polar. It's got a dipole moment pointing towards the oxygen atom and away from the carbon atom. The carbon becomes more positively charged. It looks something like this. The carbon becomes more positively charged, and the oxygen on either side becomes more negatively charged. And that means that we can display that with an image that looks something like this, where here we have blue means a lower electron density and red means a higher electron density. So we've separated the electrons and we've sort of pulled them out, and we have sort of a negative charge on the molecule here and there, and a positive charge on the molecule in the middle. But because of the way vector addition works, when we add together these two arrows, because they're pointing in exactly opposite directions, imagine them like playing a tug of war. They're equally strong and they're pulling in exactly opposite directions, and so it's not going anywhere. The overall molecule has no dipole moment because those two dipoles cancel each other out. So the dipole moment of the molecule depends on the dipole moment of each bond and upon the shape of the molecule. So a molecule like ammonia, which looks something like this. So we have a nitrogen atom in the center here, and 3 hydrogen atoms bonded around the outside, and it's shaped something like a triangular shaped pyramid. It's been squished down a little bit, so it looks like this. So this molecule, each of the hydrogen atoms is slightly positively charged, and the nitrogen atom is slightly negatively charged, because each of these bonds points in towards the nitrogen. Now if we look at it from this way, it appears like all of the vectors would cancel, except, and that's true for as far as this plane is concerned, but when we turn it, hopefully you can see that the nitrogen atom is above the plane of containing the nuclei of the 3 hydrogen atoms, which means that each of these vectors contains a vector component pointing upwards. And that means that when we add those three together, those three do not cancel. So overall, there is a polar component to this molecule. This molecule is polar, ammonia is polar, and that causes certain properties for ammonia to have. But another molecule like SO3, sulfur trioxide, is nonpolar, because in this case we have a structure that looks something like this. We've got a sulfur atom in the middle and 3 oxygen atoms around it. Now, in this case, each oxygen atom is doubly bonded to the sulfur, and that means that the whole structure has a trigonal planar geometry. It's flat. And now, the oxygen atoms are each more electronegative than the sulfur, which means that each bond is pointing outwards from the sulfur to the oxygen. But now, because they're all coplanar, that means that they do all cancel. All of those dipoles cancel. Those dipole moments cancel each other. And overall, on the whole molecule, there's no dipole moment. So sulfur trioxide is nonpolar. This is what makes sulfur trioxide a gas at room temperature. Actually, ammonia is also a gas at room temperature, but it's closer to a liquid. So that was bond polarity and dipole moment.